today I introduce Professor Ngai, a renowned expert in the field of relaxation and diffusion in complex systems. Professor Ngai is currently retired from his position in Naval Research Laboratory in Washington, and in the last 35 years, he has been visiting as a professor in several institutions all over the world, from Japan, Europe, and so on. And one of which is the University of Pisa. He started in Pisa in 2006 in Professor Rolla and now Professor Capaccioli Group. Professor Ngai received his PhD in physics at the University of Chicago in 1969. Through his career, Professor Ngai has conducted pioneering research in glass transition and relaxation dynamics in complex systems. He did theoretical research on many-body dynamics, developing a theoretical model named the coupling model, which has been able to rationalize many experimental evidences on relaxation dynamics in complex materials. He has published over 700 scientific articles in high-level journals, obtaining more than 32,000 citations. His H-index is currently 84. He is also the author of books and has received numerous awards and recognition for his work. In addition to this, Professor Ngai has been the organizer of the first international conference on relaxation in complex systems held at Virginia Tech in 1984. This conference continued in 1990, named as the International Discussion Meeting on Relaxation Complex System, which was held in Crete, so moved in Europe, and is organized by Professor Ngai every 3 years. The last one was last year, the 9th edition, in Japan. Today, Professor Ngai will talk us about universal many-body relaxation and diffusion in interacting systems, fundamental physics, and rich application. I'm sure that his presentation will be very interesting and informative for all of us. I invite you to join me in welcoming Professor Ngai, and after Nai's presentation, you will have the opportunity to ask him questions. So we can start, and let's say to the people that are connected in remote via Teams, that we are recording the seminar, this lecture, and so if they want me, they can shut down the cameras. Thank you very much. Please,
so
Professor Ngai.
Yes. First, thank you, Professor Simona Bonco and Alpido for having me here to opportunity to give a talk to the IPCF community here. When I was asked to give a talk here, I have a dilemma because I really want to talk about what I've done in the past few years, which is, as you can see on the screen there is this title, which is the same as the talk, supposed to be. It was published finally after 3 years of work in progress in material science, and it's thanks to IPCF or CNR, it's open access there. So now I benefited from definitely a lot of things from association with CNR IPCF, but particularly this one is very helpful because it's such a huge article, and so very difficult for people to access to it. So COVID, we know that changed everybody. It changes me, and but it's in a very positive way, because in 2011, that Professor Parisi in Roma got the Nobel Prize in complex systems. So he's definitely the leader in theory and very exceptional contribution to the field. I'm a lowly theoretician, not to think about comparison with such a highbrow contributions from people like not only Parisi but many people too. So my specialty is looking into experiments. In other words, I'm the one who always interested. What are you doing? can I see what you're doing? I like your data. I like to see what I can think about it. So that's why at the COVID time, starting there, I moved back from Washington to Virginia to California to a nice, beautiful, in a sense of climate-wise, beautiful place, and sit down every day. Just nothing better to do except to think how I put all these things I've done in the 45, 43 years or so or more together in a review article. Now you can see that in the slide there. I summarized there are probably the sum is 600 figures in there. But some of them are just combination 3 or 4. So the total number it could be 600, I think, and 1,300 references. These 600 figures are all experimental data. Of course, I make contact with it, but it's in a way this talk as well as this review article, it's a celebration of the hard work and so many achievements and so many our colleagues all over the world. So that's why I want to tell you. But at the same time, it's very difficult to talk about this work because there's so many areas, so many different aspects, different processes, the materials, different fields. So that's why I found out, say, okay, let me just go to a subject which restricted to a certain part, which is so-called indispensable Johari-Gosan. And the primitive relaxation is a word from my coupling model in complex materials. So these are the things I like to talk, but you can see that even this talk will not be able to complete. So I will stop roughly about 45 minutes to 50 minutes from now, so that you would be able to see some part of it. So this is what I try to do. But so let me give you the history of that. You know, I'm an old man now, but in the way that is, I started early when I was in 1979, and it's all by serendipity because I was not involved in this relaxation thing. I was in mainly in electronic properties. But you went to a talk. In this case, someone was actually, someone may know, Andrew Johnson from London. He's a dielectric man. He showed something, and he showed some data, and because of some connection with the talk, I was able to motivated to think about a way to understand what he's talking about. He's talking about a restricted area, but then I brought in, and it's called a coupling model. I won't give you the details of this thing. It's very much documented papers and in books and review articles. But the main thing is there are two basic things you need to see. One is so-called the co-Rausch relaxation, and this is 1854 from co-Rausch, but I was able to derive it from this so-called coupling model. And then I have this very important equation, which will give me all the incentive to apply to experiment. And this equations basically you see that very often now in the rest of the talk. And one is a key concept is called the independent or primitive relaxation. It's basically something which don't start out without worrying about the cooperativity of the many body dynamics. I mean, the complex system. I mean, just individual relaxation, which are simple. And then from there, this equation takes you to this many body so-called cooperative relaxation. That is, we call usually tau alpha in the case of glass forming material. So this is the equation connecting simplicity to complexity. In other words, life is very simple when you don't have interaction, and very simple. But when you have interaction or intermolecular potentials, in the case of glass formers, you get very complicated or so-called many-body cooperative dynamics. And the relaxation time have very different or very difficult and to understand sometimes properties that challenging to explain. So anyway, this is to give you that. So the history again, as I very simply starts 79, and then in connection with this so-called Johari Goldstein relaxation, in 1998, I realized that the primitive relaxation of the coupling model is actually realized in experiment as this so-called Johari Goldstein relaxation. They are important because they are everywhere too. They are also universal. So I'm saying that I have this developed this coupling model, which is 79. And I just briefly say now, it has not been changed. So for whatever 44 years or whatever has been remained the same and have been enriched by experiments. And the way I just summarize briefly, that is, again, that the idea is that coupling model is that we have a simple motion that is simple, that is not yet worry about the cooperativity or the many body or cooperative motions of interacting systems. But we have this so-called primitive relaxation. And then through this equation, which you can then relate not only quantitatively between these two quantities, but also their dependencies, that is on pressure, temperature, scattering vector, and so on and so forth. All these are linking the primitive to the many body of relaxation. So you can apply to many systems, not just gas and scission material, but also the ionics and other material, even crystalline materials, so long you have interaction. Okay, so again, quickly, I just recapture what I said earlier. That is, it was started 79, and it was already applying to this thing. Then in 1998, I realized the primitive relaxation is has a correspondent in which is the so-called Johari Goldstein relaxation, which has been very basic, of course. So I have experimental linkage between the coupling model key concept to the Johari Goldstein relaxation, which experimentally you can find. So then I found that is true. So and then the important thing is that because the primitive relaxation over here is strongly connected to the many body relaxation time. So because of connection with the primitive, with the Johari Goldstein relaxation, now we are now through this equation here, we are linking the Johari Goldstein beta relaxation to the many body relaxation in this as described by the coupling model. So there are a lot of applications then extended to the Johari Goldstein. So this is the book I published, which is this book here, which is published about more than 10 years ago now. So that was done on summarizing everything about more than 10 years ago. Then we write a book on ionics, applying the ionics, and this is totally to do with ionics here. And then this is come back to this COVID years, and instead of writing a book, it's better to publish in a review. And so was lucky that they asked me to do that, so I did that. And you can see that that's why I say I cannot give a talk like this because it has too many subjects. So we chosen that. So to show you how many subjects, just last year and this year, I have published 2 articles. Right now you can through the door you can get it, but the main point is published already online. But it's all going back to polymer dynamics of the 40, 50 years of the idea that entangled polymer chain dynamics reptate. That reptation model is very prevalent. Everybody seems to say it's settled. okay, the Digen's Edwards idea of entangled polymer chains are reptate. Okay, so that was the very nice idea, but there are problems recently found. And so I just want to say that because I'm not able to give you this volume of work on different area, I want to give you a so-called idea that is really applicable. And so that's why in the last year, after finishing the article, I returned back to look at all the past data of that have been done, either to support or not supporting reptation. And then after that, since I was believing there's a very general and universal of interacting systems, which should apply to entangled polymers. It's just insert of molecules, now you have chains. So I apply it, and the two paper, if you care to look at it, review all the experimental data. As I say, I'm a theorist, which is very important, very concerned with experiments. So that's why experiment first, theory second, and particularly when I apply it, I would know all the data already. So these two are just 2024. Okay, let me start now. What are the systems there? These practically contain many different areas of research. Many people may not be involved with too many of them, but in this case here, I am. So these are not just advertisement. Each one of them, there are involvement from the coupling model. So I will let you just take a look at it. That there are so many different material, different processes, but it all seems to conform to some universal features or properties that is on the relaxation and diffusion. That means the dynamics, okay? And some of them are related to thermodynamics too. Okay, so that's a thing. So I return now to this area only for glass sensation and Johari-Goldstein relaxation. So now I no longer talk about generality. I focus on this part. Well known in this case, so-called everybody knows the alpha relaxation, and there's a beta relaxation. There are many second relaxations, so not all of them are important. The one important in this case is we call it Johari-Goldstein relaxation. How you define it is the one that is related to the coupling model primitive relaxation. That is the definition for me for Johari-Goldstein relaxation. Other people may see other relaxation which are not important because they are intramolecular. They just within the molecule itself. It's not intermolecular, that kind of a second relaxation. So that is the thing. So you can see what I'm trying to do. You see this slice here. I try to put tau 0 and tau beta, which is Johari-Goldstein second relaxation time, together in a formula, which is characteristic of the coupling model, and then put it into experimental regime, because now people can experiment, can look at this tau beta, look at tau alpha. They can look at the relation between these two in terms of quantitatively at a certain temperature, how they are related, how the pressure, temperature, and other dependencies of the two are related. So this equation is very useful, very easy to apply. I forgot to say one thing, because many of the work I benefit here is my association with University of Pisa, first with Roller's group, with Simone Capaccioli, particularly continue to now, and with Johari, of course, in a way, because stimulation with LPDO. So I benefit so much from Pisa. I mean, both institutions here. So I forgot to say that, because in particular, this one is so much work being done. You see some of them. So now these are items I try to present in a talk in Japan, but then it would not be possible here. So these are items here related to this specific subject. So let me tell you about this first thing about the presence of this so-called primitive hydraulic relaxation, and show you they are the same as done in various material processes. So number one, okay, so this is very elegant experiment now, only recently done by the group in Trento, collaboration with Simone. And then the way they use this very advanced methods of so-called TDI, time domain interferometry, and they're able to look at the dynamics in a very microscopic way. They see the alpha relaxation in this picture here is over here, and then they look at the different Q, so-called the structure factor. They look at different, they found at the high Q, which is local, they found this relaxation, which is the Johann-Goldstein relaxation. You can do it by dielectric too. So dielectric, you can see that, see the alpha relaxation and the JG relaxation. This is a different, this is a monohydric alcohol data here, but they did it for many material like ortho-sulfonyl, which is a molecular glass former. They did for polymer. These are very recent advances, and even for CKN, calcium, potassium, nitrate. So all these are very important, but they are microscopic. And so when you find them, these are different Qs or different sizes you like, or different length scale, but they are very local. And when you find that the most local one, and then apply the coupling model, you will see that the data here, the primitive relaxation, the golden circles here, right there with the thing. So this is a very good example of seeing how coupling model work with Johann-Goldstein with experiment. You see them right there, and you know the Q, and it's very large Q here. Somewhere here is very local. In other words, these are really the simple motion that start the eventually to go to the cooperative motion that would everybody is focused. We're focused on, but no. But where you have to worry about the beginning. In other words, you think about the origin of this cooperativity. You must understand the beginning, and particularly the relation of these two these properties are very specific, very quantitative. Okay, so these are more experiments showing other type of, even in glycerol, this old workhorse, which they did it again, and they found the same thing in in the more other material. Okay, so this is a good one to show you. This is a plastic crystal. It's not like ordinary glycerol molecule or not a polymer. It's a plastic crystal, and you see the structure here. They are in translationally, they are ordered, but then orientationally, they are disordered. There's a dipole moment here, and here you can probe that by dielectric, which is done by the group of Tamari. I think Simone is a co-author of this paper too. And then you see dielectrically, you see the alpha, see the beta, so-called the JG relaxation here. And so this you know the coupling parameter in the coupling model equation. This one here, you see the 1 minus n, that is the Kohlrausch exponent, as I mentioned already, which is also part of the coupling model. And then when you look at this equation, you can calculate with a known exponent here, because it's known. You can see that 1 minus n is plotted out as a function of temperature. And then you know the alpha relaxation time, which is now given here in the relaxation map, together with the beta relaxation down further in the lower temperature. They found this Arrhenius one. Okay, then I can operate with this beautiful experimental data. All the known parameters, 1 minus n is known here. And then you know the TC is known. This is from neutron scattering before. For many of these material here, TC is about 1 picosecond. So we know this number. This is also from the coupling model too, but experimentally determined from neutron scattering or by other means here that determine this quantity here. I wouldn't explain furthermore the reason for this TC to be a constant value, but that's a known quantity. So use this right-hand side of this equation. Everything is known. No, I'm sorry. No, it's not known. So what you need to know is the so-called from the alpha relaxation time, you calculate tau zero. You become two parts. One is the activation energy part, and the other one the prefactor part. So both of them you can check with experiment. You can calculate from tau alpha all these quantity here. So from tau alpha, you know this, you can deduce it, and so everything works out just as expected, as like this. So it's completely verified. I won't go through the detail, but it's both are verified. The connection is very nicely done. So let's go to another one is metallic glasses. Metallic glasses, people find the again this Johari-Goldstein relaxation here, the JG relaxation here at the alpha. You know, metallic glasses were different. You know, it's entirely different structure and relaxation kind of behavior. And when you do a very good simulation, like done by our Chinese colleague, Haibin Yu, and he did this simulation here, he found exactly this beta relaxation, the alpha relaxation. When we calculate this coupling model, and now it's 0.2 picosecond for metallic glasses. Why? Metallic glasses much stronger interaction compared with van der Waals liquid, much weaker. So that's why TC is different, but this is also known too. It's not just a fitting parameter. So when you do that, you get the very nice agreement with his the circle here with his simulation too. Okay, so I wouldn't go there. It would we work. I benefit the work with Simone and Pacciaroni from Perugia, starting out to go to water and hydrophilic material as well as hydrated biomolecule. Again, you see those things are in this simple figure here. They are there. The geological signs there, and then the alpha relation is also accepted. So let's go to the next one. The next one is this is very cute. This is the invariance of the Johari-Goldstein or beta relaxation to changes the pressure and temperature at fixed value of tau alpha. So you do experiment, you choose the pressure and temperature, and you can vary the combination, but you keep the alpha relaxation time constant. Okay, that's easily done experimentally by easy. I mean, you can do it. And then you look at what the tau beta is doing. Is it, if you keep the tau alpha constant, is it tau beta sometimes change here, sometimes go there? No, it turns out they always kept the same relation to that. So let's look at data. So these are, for example, data. First thing is that, oh, I forgot to say that. First thing is already amazing that you do experiment like this typical one. When you do different pressure and temperature combination, the alpha relaxating peak, you see the peak here, we call it the frequency dispersion. Now, these are different combination of pressure and temperature. Sorry, it's too small, but you see that there are many different combinations, and they're very different. Sometimes you apply pressure up to 1 gigapascal, which is very large, high pressure, because normal pressure is 0.1 megapascal. So all is a magnitude change. You change the temperature to adjust to make the same peak here, but then they superpose. It's beautiful. Now this is also predicted coupling model. There's no other model I know of predicted this thing. The coupling model equation predicted that. So I won't go to that. You have to read the review, but it's explained there. You will not it was surprising, right? Why this thing so? But more than that, this is the next part, the next one. I said that the alpha beta are kept the same place. Look at this one, for example, is done by Simone actually. You see that the alpha is the same shape, of course, but then you see the beta is also there all the time, remaining this relatively close. I mean, the same relation to the alpha, the same relation. Now, this is not the only one. Let me go to a next one. This is the best. This is done again by in Roller's group under supervision by a very brilliant woman's student. She did this. It's a mixture of so-called quinidine, which is a polymer molecule like this, in tristirene, which is apolar. So you don't see the tristirene dielectric. What they have done is many different pressure and temperature. See this track here, pressure, temperature, and you see that they are again the same. The alpha remain the same shape, and which is again the I already said about, but the so-called the JG remain the same place. Now the relaxation strength is not the same, but you can see that they remain the same. And you calculate coupling model using the equation here, you get this same place, nearly the same, the peak position as the experimental relaxation time. So this equation here already guarantee you that not only that this is constant, the shape is constant, but also this relation between tau 0 and tau alpha is the same. If you keep this the same, because this n doesn't change, the shape doesn't change, means that the co-Rausch exponent 1 minus n doesn't change. So this doesn't change. This is a constant. N doesn't change. 1 minus n doesn't change. So that means these two have to be kept the same. So in other words, the coupling model predict this behavior of the behavior of the JG relaxation, which is realized in experiment. So I mean, this is theory which do that, but because of this relation here, is because we found this partners, the primitive and the JG are partners. So everything is verified nicely here in this experiment. So there are more experiments, different representation. Again, I wouldn't go to detail, but you can see from here, whenever you change pressure and temperature, in here you change temperature only, and you see that the alpha beta remain the same whenever at TG, which is a fixed 100 seconds, the same place. They are all the same. You can vary now different pressure, and then again same thing, they remain. This is a different representation, but show how general it is. And this is I won't go to this except this side. This is the same thing as done in Roller's lab. So this one is known already, but this one is interesting. This is totally different. This is ionic liquid, room temperature ion liquid. So this one is a no longer molecule. These are two ions, which is silicon base, huge molecule. The cation and the anion is BF4 and is cation. So this conductivity. Again, this conductivity is also simple motion. The simple motion before the ions are correlated together and move together, and that's we can also call the alpha and the so-called the analog of the JG of the relaxation, which is ionic now. So you do that experiment and you see the so-called the primitive, the so-called the primary conductive relaxation peak. This is experimental by also done by dielectric. This is M double prime. This is no longer epsilon double prime. This is more electric modulus to represent ionic. And you see the secondary relaxation. And then you see that they are, when you put the pressure temperature together like this, I mean, they are blue and red. They are two different combinations. You see that they are the same place, the same shape, the same place. And so when you calculate coupling model, tau 0, which is now F0 because it's frequency, but it's just 1/2 pi tau 0, and you find the same place, near the same place. So everything is just working like molecular systems, and even though now it's ionic. Okay, now this is simulation. Very well done by Petrov. Petrov and Smith. They take this so-called chain, and then they put this together to have interaction by the Leonard-Jones potential. They found the beta relaxation, the alpha relaxation, and then all that is also they put pressure on it, and then this is a pressure. This is simulation, but pressure, they can do it. This is different pressure. Beta, alpha, superpose perfectly in this case for this combination, and different combination also superpose perfectly. So now it's a toy system, is what you call it, rod and ball bit spring model, bit lattice model, but it's a perfectly done and done well. So it's done simulation. I collaborate with a Chinese group that do very good simulation in metallic glasses, and then we found the same thing. I won't bore you with that detail, but it's there. So it's again different combination of pressure, temperature, and in this case the mean square displacement. But it's another way of showing alpha, beta in a way, and it's the same thing. Okay, so let me skip a little bit. So now let's come the next one. This now related to thermodynamics a little bit. So let me make sure I cover this part, and that is both tau alpha and tau beta. Now, whenever I mention tau beta, you should I would like to remind you this is tau 0 too. Tau 0 and tau beta are just hand in hand. They are related. They are cousins, you like. They are related. So, brothers. I mean, brothers. So the two are the same thing in a way. These are functions of so-called thermodynamic scaling variable. Rho is the density. Gamma is a so-called exponent. Is a dependent material. It's a material dependent constant. I'll explain to you why. And T is temperature, of course. So this involves thermodynamics, involving the not only just relaxation, but now involving density. So so it's already go beyond just dynamics alone. Okay, what is this about? Okay, so what you do then is people do experiment with pressure and temperature, of course. They also know the equation of state, PVT. So they know the volume, pressure, temperature. Then when they did experiment on different combinations, they can go back to look at this variable, T rho. Actually, in this case, they use the volume, but volume is the reciprocal of density. So it's the same thing. So sometimes people use so-called TV gamma instead of rho gamma T. I mean, this is the same thing anyway. It's different way of showing it. So you did an old experiment like this case done in Tamarit's group in Barcelona by Romanini. Then what they did is that they look at the alpha, look at the tau, look at the beta. Before you, this is the 10 to minus 4 gigapascal is basically room pressure, and they find this alpha and tau 0. I mean, so JG, and when they test the coupling model, is right there. So this tau 0 is the same thing. It always works. That's why. And also this gamma is nonsense. We don't need to worry about it. It's a very local motion. Okay, so you do a 0.4 gigapascal. You raise it by how many? Four orders of magnitude of pressure. You do the experiment with higher temperature. You also get the same good correspondence with tau 0. And that's the JG, and that's the alpha. Now, So they know PVT, they know pressure, volume, and they transform this data in terms of this variable by a gamma, which they chosen to be they find to 0.2 is the best, and they can scale everything together on the same plot with both of them have the same so-called TV gamma dependence. The dependence is different, of course, but they all depend on the same variable. So what does it mean? It means that if they have the same thermodynamic dependence, it means that the JG relaxation or the primitive relaxation is very basic because it starts to have that density or volume dependence already at this early stage of the relaxation process. You think in terms of causality, I mean, things are happening because you have something earlier. Okay, so the JG is earlier process. It's an earlier process. So, and it has the thermodynamic dependency already on the volume or density. And because the same variable can do that. Now, so you can see that why this is interesting and important because it tells you one more thing. Not only beta, JG, and alpha are coupled together in an intimate way, as you see, you saw pressure changes, temperature, they maintain the same place, same relation, but also they have the same dependency on the thermodynamic variable. In this case, is volume or density. Okay, this is general now. You see that? This is done by Casalini and Roland in my lab in Washington, D.C. here. And so they do PMMA. This is polymer. And the alpha and beta there. Again, you look at the bottom is a T row 1 point whatever, 94. So gamma is about 2 again. And this again, you can scale the whole thing together with the same variable. Again, the JG relaxation has very important fundamental meaning. I'm not only meaning, a very important relation. You cannot forget it because you cannot forget the something before you. Because that is happening before you go to the cooperative alpha relaxation. Okay, so that's a very important implication. So this is again another case of what do you call it, metallic glasses. Same thing. We did the simulation and we found the same thing for the variable, dynamic variable, which is related to the JG relaxation. This is called tau alpha 2, which is called the non-Gaussian parameter, but it's related to the JG relaxation. This is diffusion. So both of them are doing the same. This is the long-term diffusion, and this is the Fickian diffusion of the atoms here. So they all have the same gamma. Okay, same gamma 1.64. So very general. This is I won't go to that detail, but it just mentioned there is a basic theory behind that to tell you why the relaxation time have depended on TV gamma. And that is due to the fact when you have potential, which is purely inverse power law, repulsive. From thermodynamic, from statistical mechanics done by, let's say, you go to this paper, for example, they proven then everything, the relaxation time should have the functional form, and the dependence is on TV gamma, or this is a rigorous result. But reality, even in the van der Waals liquid, van der Waals molecule liquids there, it's not purely repulsive. You have the other term, attractive term. That's why the Leonard-Jones is 12.6 potential. But even so, this attractive part is there. It's pretty close to this prediction here because somehow this is determining this relation. I'll tell you why, because this is a way to do it. this is the potential now for this Leonard-Jones system here. It turns out that that gamma is very much at the very short time, short distance. This is G of R is a structure factor. Okay, this is distance R, G of R. And so these are the G of R, sorry, the G of R. And this is the potential that is used, okay, in this simulation here. You find that the gamma is determined by the slope here, the repulsive part. It is very short distance. You see that this is the main peak here, very short distance. It tells you why the JG is already have the TV gamma dependence, because it's already a short distance. They are determining that, and so I won't go to the details here. Oh, okay, simulation thing. So again, you see, this is the G of R for this 1,4-polybutadiene, okay, done by this the Greek group there, and you see that the potential here, the potential is for polymers more complicated, but this is the repulsive part, and you see the slope here. When they do the slope, when they do the scaling, the slope of gamma here, the gamma is right here at this short time again. So this is the same thing as this one, and it's very short time, very short distance, sorry. So again, related to that. So all these things are telling you that is so. So let me make sure I'm okay. So let me go to one last topic, which is the confinement. So you go to nano now. So bulk is, oh yeah, very, very cooperative. If I make it nano confined, the length scale is much smaller now. Okay, you make it so small and the cooperativity cannot develop. So what you get back? You get back the primitive relaxation according to coupling model. Or you get back the JG relaxation approximately for all the bulk. So you can check that. So let's do that. So this is the one. So let's do several of them. So modification, nano confinement. So for the coupling model, if you make the intermolecular coupling go to 0, when n goes 0, then you can predict that the tau alpha at nano confinement will be just the tau 0, which I know I can calculate from the coupling model, or tau JG right here. So this is the reason why I can predict from the coupling model on nano confinement. So there are three cases. For example, let me give you one at a time. This is the case of ultra thin film, polymethyl phenylsiloxane. Okay, so this is the one. The data are done by Anastasiades, and this is alpha for the bulk. Okay, and so the alpha bulk is tau beta is known too. This is tau beta. So this is JG. So when they did the thin film intercalate into this, the become very thin film, 2 nanometer thin film, you expect, as I said, the coupling model n goes to 0. As I told you already, tau alpha should you instead of seeing tau alpha, you see tau 0. So what is tau 0? You can calculate it because we know from the experiment the n value is 0.48. In other words, you can calculate the bulk material, and you know the coupling parameter or the co-Rausch parameter, and the n is 0.48. There's no fitting parameter. So use the equation and calculate that, and there you are. You find for three different temperatures, bam, here and this one, you calculate that, it becomes these 3 points. It's exactly in good agreement, or in very good agreement with tau beta. So you have proven it. So is this general? Let's go to this one is more complicated, but let me don't skip this because in view of time. So this one is even simpler. This is it's a pharmaceutical. It's for it's what you call PLG, pilocaine. Pilocaine is, I think, is a pharmaceutical, and the structure is here. And this is done for the bulk dielectrically. over a long, over extended relaxation time range is the bulk. Okay, different measurements of the bulk. Okay, when they confine it in 1 nanometer pores, very small now. So they found this relation. They found the black circles. You see, black circles here, and some of them are other data. No, just only one set data. So from here, from different sets of bulk relaxation time, I use the coupling model again. So the tau alpha is known, n is known because they already characterized the bulk. They know the shape, they fit it with the Corrales function. So once you do that, I can do that immediately. So it just takes only about 10 minutes. And you calculate each point, each data point with that. And you see lots of other points which is straddling the black circles here. So these are tau zero calculated with from different measurements with the same material, and it's right there. So this is one, and you say, well, is it general? Yeah, well, it is. And this is done by the group at by Luke and Amyloido's group, and they did it from again the old friend Grisero. Everybody loves Grisero, even though it's such a workhorse. And they do it again the same way by finding in 1.16 nanometers sea light in the Amazon framework. This is a very high-tech material. You can put it in there. 1.1 nanometer, very confined. So even Grisero, you know the N value. You see, this is experimental for the bulk. So this is the bulk tau alpha. Okay, you can calculate that. So tau zero is calculated with the blue one, and the experimental confined, when you confine it, is a square, a red square, is right there again. So it's again, even very different materials, the same thing. So I just concluded with an entirely different material. This is so-called yttria stabilized zirconia, which is a energy storage material. Okay, so this one, you get the bulk again, make it simple for you, the bulk relaxation time. This is a conductivity relaxation time. And then you can now make it smaller. This is a make it smaller. This is almost like the bulk. So you go to this is relaxation, this is a conductivity, sorry. And this is temperature. The conductivity, when you make it thinner and smaller, the thickness become on a substrate. When the thickness become smaller, this is a different thickness. This is almost like bulk. When you become thickness becomes very small. In this case, 50 nanometer thin there on the surface, also on the surface too. If the conductivity rises, the activation energy changes. It no longer is that much. This activation energy is like the bulk. So it's like here. When you convert conductivity to relaxation time, of course, this is the conductivity, and the right side is conductive relaxation time. But there's a formula for it, so it's the same thing. Okay, so you see the activation energy is the same as this one for the bulk. Okay, when you go to here, it's conductivity is much lower activation energy. Okay, so what do you find? You find this thing here. This arrow here is the same arrow as the same length as the change from here to here when you convert conductivity changes to relaxation time change. Okay, and this is tau zero calculated from each of these points here. Okay, so one last thing now I'll quit is that you can calculate tau zero from this tau alpha, all conductivity. This is due to oxygen conductivity, oxygen hopping. And then you go to this, you get this value here. Activation energy is much smaller because of relation of the two as defined as a predicted coupling model. And you extract this thing, both of this thing to infinite temperature. You look at this one with the bulk. They are going to 10 to minus 17 seconds. which is very unphysical. You don't have vibration or temp frequencies of the ion whistle. Only we know it already by the Raman scattering. The oxygen atom is known by Raman. It's over here, 10 to the minus 13.5, the main peak here. That's the oxygen vibrational attempt here. So how can you understand this? You can't, because this is cooperativity. It's always abnormal. Right? It give you this, give you a large active energy. When you go to the tau zero, you can understand the thin film because now becoming non-cooperative. On the surface, they can move around freely. But also this one, look what it does. It extrapolates down to 10 to the minus 13.7, almost the same as this temp frequency. So you can understand why simple physics from a non-cooperative or a simple motion that has all the properties that you can understand or easy or better understand. But when you go to cooperative system like alpha relaxation or gas form material or ionic, in this case, totally different system, and they are complicated. They are because of that cooperativity, because interaction like that. And the coupling model is able to capture that. Okay, so I think I'm done already because I'm not going to go to this item. Even this subject is limited to this. So I would summarize in terms of a few words or some statements. What I'm trying to show to you is that there are many beautiful experimental facts lying there. It's very difficult for anyone to assemble them together. It takes a lot of work, and lots of people cannot do that. I was lucky in a way because I work at Naval Research Lab. It's a government laboratory, and I don't need to get funds. I need to every year to justify that I'm doing okay. But I don't need to say apply for funds because to apply for funds, you need to be looking good. Looking good is that you are doing a very fashionable or timely thing. I don't need to. So you can see that for 45 years now, because 79 to now is 45 years. I was, of course, I retired from Naval Research Lab. I don't want to every day to drive the car 45 minutes to and then come back. I retire and still can work. That's why I so benefited with association with IPCF. Very people in this organization here. But that's because I was able have the lucky enough. I don't need to please anyone I can keep on doing the same thing. Assemble the beautiful experiment. Don't believe what I can do. Okay, don't take my coupling model. Don't worry about my phone from the United States. So what I'm trying to tell you is that look at this data. 600 figures. You look at them. You decide yourself. And maybe somebody else will provide a much better and more believable way to understand this. But the facts are there. And I assemble as much as I can into the progress in material science review. It's for people to look at. Unfortunately, I think most people would be horrified looking at that review. I myself, sometimes when I look back at it, oh my God, where do I find? But okay, as I told Daniele, who's sitting there, this review is very useful because there's a search there and you click on in the PDF, of course, a word or a name or a subject. You go there, you find something, which is to do. As I said, I don't want to emphasize the coupling model in this review. I emphasize the experiment. So you find the nice thing. So this is my so-called concluding remark. It's all for a so-called appreciation of my association with IPCF and University of Pisa. Thank you.
Thanks a lot. Thanks. Thanks a lot for this contribution.